When we talk about the total angular momentum of electrons, it's very important to determine this properly because this is going to tell us the magnetic moment of an atom. And it is affected by three possible types of interaction. So we can have spin interactions, spin orbit interactions, and orbit-orbit interactions. So these couplings will affect the value of the total angular momentum that we calculate. For example, if we talk about spin-spin interactions and orbit-orbit interactions, so in light atoms where we have negligible spin-orbit coupling, these two interactions are dominant, and that leads us to the Russell-Saunders coupling scheme. And if we have spin-orbit interactions as the dominant term, then this is going to take us to JJ coupling scheme. So the Russell-Saunders coupling is effective in light atoms, and JJ coupling, the spin-orbit coupling, as we have seen in the previous video, is going to be dominant in heavy atoms. So this is going to basically tell us how we're going to add the angular momenta of the electrons. And why are we trying to calculate the total angular momentum? Because the total angular momentum is going to determine the magnetic moment per atom. It will also tell us whether or not it's possible to have a permanent magnetic dipole moment in an atom. So let's start with Russell-Saunders coupling. Now, as I said, this is in light atoms where the spin-orbit interaction is weak. The coupling between orbit and the spin-orbit coupling is not the dominant term here. So it's the coupling between individual orbital angular momenta, and the coupling between individual spin angular momenta should be considered, so that's the stronger term. So this is going to lead us to a recipe to calculate the total angular momentum, and the recipe is as follows. The first step is to combine the orbital angular momenta of individual electrons. So combine the orbital angular momenta of all the electrons. When I say combine, this is a vector addition, basically. The second step is to combine the spin angular momenta of all the electrons. Again, vector addition. And the third step would be to combine the total spin and total orbital angular momenta. So let's demonstrate this for a two-electron system. So we're going to add the angular momenta of two electrons using the Russell-Saunders coupling scheme. So our first electron, electron 1, has an orbital quantum number or orbital angular momentum quantum number L1. Now this means that the angular momentum vector L1 magnitude is square root L1, L1 plus 1 h bar, and its z component is m sub L1 h bar. And for the second electron, electron number 2, I have orbital quantum number L2. The magnitude of the angular momentum vector is square root L2, L2 plus 1 h bar. Its z component is m sub L2 h bar. That is the component in the direction of the applied field. Now, what are the allowed values of the total orbital angular momentum? The allowed values of L total is basically given by the Clebsch-Gordon series, and for this two electron system it's going to be a value between L1 plus L2 and absolute value of L1 minus L2. The corresponding total angular momentum magnitude is square root of L plus 1 h bar, and the corresponding z component of the total angular momentum will be equal to m sub L capital L h bar, where m sub L can take values similar to the one electron case, minus L plus 1, L minus 1 plus L. So we have for the two electron system, the individual orbital angular momenta are summed up in such a way that the total angular momentum quantum number L, capital L, is given by a value, an integer value between the sum and absolute value of the difference between the two orbital quantum numbers, and m sub L varies between minus capital L and plus capital L, and it's an integer. And so we have accomplished the addition of the orbital angular momentum momenta, and for spins of these two electrons we have the total spin angular momentum quantum number capital S is equal to one of two values, S1 plus S2 or S1 minus S2, which is either 1 or 0, because remember S is equal to 1/2. And the corresponding magnitude of the spin angular momentum is square root capital S plus 1 h bar, and m sub capital S is going to be a value between minus S and plus S, and so this will take values in this case minus 1, 0 and plus 1. The corresponding z component of the total spin angular momentum magnitude will be m sub S h bar. So this is how we add the spin angular momenta for the two electron system. And now let's take a look at a specific case. So for example, let's consider the following case. We have L1 is equal to 2, so it's a d orbital electron, and L2 is equal to 1. So in this case, the total orbital quantum number, capital L, can be 3, 2, 1, and m sub L, capital L, can be -3, -2, -1, 0, 1, 2, and 3. And as for the spin, we have the first spin quantum number is 1 over 2, the second one is 1 over 2, the total is 1 or 0. So you can see that when I add these angular momentum vectors, so you have one angular momentum vector here, that is L1, and the other angular momentum here is corresponding to that of L2. So this has a magnitude square root L1, L1 plus 1 h bar, and L2 vector has a magnitude square root 2 h bar, 1, 1 plus 1. And the total one, if you add them up, you get the total angular momentum vector L, which has a quantum number L is equal to 3. So that's one way to add them up. And then you can have L1 vector like this, and L2 vector like that. So you subtract them, and then you obtain basically a vector capital L which has a magnitude L is equal to 1. And if you have if you want to consider capital L is equal to 2 case, then you can think of this as you're adding the L1 vector with the L2 vector, so that you obtain the capital L vector, where capital L is equal to 2. And so this is going to be an isosceles triangle in this case. So it is a vector addition. And for the spin angular momentum, we can think of two possible scenarios here. S1 and S2 spin angular momenta vectors are added, so you get a total S vector like this, and S1 and S2 are in opposite directions, so you obtain total S is equal to 0. So these are the two possible scenarios. Then according to the Russell-Saunders coupling scheme, the last thing to do is to combine the total spin and total orbital angular momenta. Then we can calculate the total angular momentum, total angular momentum quantum number. And using the recipe of Russell-Saunders, we find that the total angular momentum quantum number, capital J, is an integer value between L plus S and absolute value of capital L minus capital S, and the corresponding magnetic quantum number, m sub J, will be a value between minus J all the way up to plus J. And Therefore, we're going to find out that the total angular momentum magnitude will be equal to square root capital J plus 1 h bar, and its component in the direction of the field, z-axis, will be total magnetic quantum number m sub j times h bar. Now we have two important remarks regarding this scheme. So the first remark is that when you consider the energy difference between states with different total angular momentum quantum numbers, so we're considering the energy difference between states with different capital J values but same L and S values. So total orbital angular momentum quantum number and total spin quantum number are the same, then the energy difference between these states will be small compared to those with also different total L and total S values. So we're going to find that if the J value is different for two states, but they have the same capital L and capital S values. As you know, we have a set of J values possible for a given capital L and capital S value. So if you look at the energies of these states, so this is state 1, this is state 2, etc., and we compare their energies, we find that these states will have a small difference in energy compared to those that have a different capital L and S values. The second remark has to do with a field shell of electrons. So if you consider a field shell of electrons, and let's demonstrate this as an example, I can use here the following configuration: 1s2, 2s2, 2p6. Okay, so I have n is equal to 2, L can be 0 and 1, so these are s and p orbitals. So if you consider s electrons, now for s electrons I have L1 is equal to 0, L2 is equal to 0. So if I add them up, I'm going to get a total L is equal to 0. And S1, if S1 is 1/2, S2 is 1/2, we must have opposite values of m sub s. So m sub s1 will be 1/2, but m sub s2 will be minus 1/2. So where does this come from? Pauli exclusion principle. So if you have electrons in the same orbital, s electrons, they have the same n value, they have the same L value, they have the same m sub L value. So m sub L1 is equal to m sub L2 is equal to 0. So they must have a different spin quantum number. So S is fixed, it's 1/2, but m sub S can be plus 1/2 or minus 1/2. So this should be different for these two electrons. So what is the total m sub s. So m sub s has to be 0, and that means the total spin quantum number s, which can be normally 1 or 0, has to be 0 because m sub s has to be 0. So we find that both total L is 0, total S is 0. So the only value you can have for J has to be 0. So we cannot have a non-zero total angular momentum for the closed shell s electrons. Now if you consider p electrons, for the p electrons we have the L value is 1, which is basically telling us that if you consider two electrons with L1 equals 1 and L2 equals 1, total L value can be 2, 1, or 0. Now, if you consider the fact that the m sub L values for these electrons should be m sub L1 is minus 1, 0, 1, and m sub L value for the second electron is minus 1, 0, 1. If you calculate the total m sub L value, since you're going to have two electrons, so two electrons with m sub L is equal to minus 1, two electrons with m sub L is equal to 0, and two electrons with m sub L is equal to plus 1. This is px orbital, py orbital, pz orbital. Total m sub L must be basically 2 times minus 1, 2 times 0, 2 times 1, so it has to be 0. So since the total magnetic quantum number m sub capital L has to be 0, this implies that for the total angular momentum capital L for 6 electrons has to be 0 as well. So we find that L total for 6 electrons, all p electrons, this has to add up to 0 as well. Now we also have the total S is going to be equal to 0 as well, because we must have the total m sub s is equal to 0. For these 2px electrons, we're going to have up spin, down spin, 2py, up spin, down spin, 2pz, up spin, down spin. So we're going to get a total spin quantum number equal to 0. And for the total spin magnetic quantum number, m sub s, we must have 0 as well. So L is equal to 0, S is equal to 0, and then we find J is equal to 0. So the conclusion is that for a filled shell of electrons, the total orbital angular momentum L, the spin angular momentum, total spin angular momentum quantum number S, and total angular momentum quantum number J values are 0. So no net angular momentum, and what is the implication of this in magnetism? The implication is that no contribution to the permanent magnetic dipole moment. So basically we find out that if an atom has no incomplete shells, if all the shells are complete, it cannot have a permanent magnetic dipole moment. So you can think of which elements have a closed shell in the periodic table. These are basically, for example, noble gases, and noble gases are diamagnetic. So we have no spin and no orbital angular momentum contribution, and there is no permanent magnetic dipole moment. And as a result, the closed shell atoms tend to be diamagnetic. So let's write this important result. If an atom has no incomplete shells, it cannot have a permanent magnetic dipole moment. For example, if you think about noble gases where we have complete shells like helium, argon, etc., they are diamagnetic. They cannot have a permanent magnetic dipole moment. Okay, the second scenario is the JJ coupling. So this is where we have heavy atoms, so spin orbit coupling is strong, and we have to consider the addition of individual orbital angular momentum and spin angular momentum vectors for each electron. So this is in the limit of strong spin orbit coupling, and the recipe is modified as follows. First, add the spin and orbital angular momenta of individual electrons. Then add the total angular momentum, total angular momenta of all electrons. So first we have to calculate for the ith electron what is the total angular momentum. It's Li plus Si, and then we have the total angular momentum quantum number J is sum of the individual electron total angular momentum quantum numbers. And this again will give us the same result. Filled shells have zero net angular momentum. So that result doesn't change in the JJ coupling scheme. Okay, so let's review what we said. We're interested in calculating how to find the total angular momentum. And why are we interested in doing that? Well, we're going to see that the total magnetic moment M will be determined by minus lambda factor Bohr magneton times M sub J. So we're going to get back to this in a little while. So we find that we need the total angular momentum quantum number, especially the magnetic total magnetic quantum number. So we have three possible types of interaction we can consider: spin-spin, spin-orbit, and orbit-orbit interaction. In light atoms, where we have spin-spin and orbit-orbit interactions dominant, we use Russell-Saunders coupling scheme. If we have spin-orbit coupling as the dominant term, then we use JJ coupling scheme. This is correct for heavy atoms. And in the Russell-Saunders coupling, we combine the orbital angular momenta of all electrons, and then we combine the spin angular momenta of all electrons, and then we add the total spin and total orbital angular momenta to get the total angular momentum quantum number, capital J. If you have a two electron system, for example, with orbital quantum number L1 and L2, then we have the corresponding vector magnitude square root L1 plus L1 L1 plus 1 h bar, and the corresponding orbital angular momentum in the direction of the field magnitude m sub L1 h bar, and similarly for the second electron. The allowed values of the total orbital angular momentum given by Clebsch-Gordon series is L1 plus L2 all the way down to the difference L1 minus L2. And m sub capital L, the total magnetic quantum number is orbital magnetic quantum number will be minus L2 plus L. And this is a simple vector addition. For spins, we have the same situation. Since the spin quantum number has to be 1/2, the total spin quantum number can be 1 or 0, and m sub s is again similarly between minus s and plus s, so it can be minus 1, 0, and 1 for our two electron system. So here you can see this is really a vector addition of the angular momentum vectors. Then the total angular momentum quantum number is a value between absolute value of capital L minus capital S and L plus S, and m sub j, the total magnetic quantum number, is between minus j and plus j. So basically we can find the total contribution to the total magnetic moment using the total angular momentum projection onto the field axis, which has a magnitude m sub capital J h bar. Now I had two remarks. If you have different J values for the same set of capital L and capital S values, the energy difference is not significant compared to having different capital L and capital S values as well. And the second remark has to do with field shell of electrons. In a field shell of electrons, if you consider the total magnetic quantum number m sub L, this has to be 0, because you have in the case of s electrons, the L value is 0, so capital L has to be 0, and corresponding m sub L has to be 0. In the case of p electrons, where we have m sub L has the possibility of being minus 1, 0, and 1, this is for 6 electrons in the closed shell, 2 of them with minus 1, 2 of them with 0, 2 of them with plus 1. The addition will give us no projection onto the field axis, so m sub capital L has to be 0, and m sub L has to be 0 only if the total angular momentum capital L has to be 0. So we find that capital L is 0. Capital S is also 0 because of Pauli exclusion. All electrons in the same orbital must have opposite spins, so the total spin quantum number has to be 0. So we find that capital L is 0, capital S is 0, capital J then has to be 0. So for a field shell of electrons, there is no net angular momentum and no contribution to a permanent magnetic dipole moment. So this closed shell, for example, noble gases fall into this category, and they are diamagnetic closed shell atoms. If the atom is a heavy atom, we have a large Z value, we have strong spin orbit coupling, then the addition scheme changes. We have to add for an individual electron the spin and orbital angular momenta, and then we have to find the total angular momentum of all the electrons by adding up the total angular momentum of individual electrons. And again, the same result applies. The filled shells have zero net angular momentum. Also in the JJ coupling